Now, for another indeterminate form, we also have indeterminate products, and these are things of the form 0 times infinity. And again, what we're going to need to be able to do is take this and rewrite it so that we can apply L'Hopital's rule to it. So let's just jump in with an example here. So the limit as x goes to infinity of x times the tangent of 1 over x. So as x goes to infinity here, we have something going off to infinity times the tangent of something going off to 0, because the limit of 1 over x is going to go to 0. So this is going to be an infinity times 0 thing. So what we need to do is be able to rewrite it as a quotient. And it's going to call on a technique that we've done before, which is sort of dividing out or multiplying by a fancy 1. So what I want to do is take this and rewrite it so this x shows up in the denominator. So what I'm going to do is just multiply by 1 over x, thinking of this maybe as over 1. And now up here, this x times this 1 over x will cancel each other because x is going off to infinity. I don't have to worry about any division by 0 here. And so this is going to equal the limit as x goes to infinity of tangent of 1 over x over the function 1 over x. And now as x goes to an infinity, we get tangent of 0 and then something going to 0. So this is of the form 0 over 0. So we're allowed to now apply L'Hopital's rule to this thing. So we go ahead and take the derivative of the top and take the derivative of the bottom. So L'Hopital's rule tells us that we have the limit as x goes to infinity. Derivative of tangent is secant squared, so we have secant squared of 1 over x times the derivative of 1 over x. So remember, 1 over x we think of as x to the negative 1. So when we take the derivative, we get negative 1 x to the negative 2. So this will just be negative 1 over x squared. And then that's convenient because we are also taking that in the denominator here. And so we have negative 1 over x squared when we take the derivative of this 1 over x here. This 1 over x squared up here came from the chain rule. And so now as x goes to infinity, these are going to cancel. And so we have the limit as x goes to infinity of secant squared of 1 over x. And as x goes to 0, this becomes the secant squared of 0. And secant squared of 0 is 1 squared, which is 1. So as x goes to infinity, this limit is actually just going to equal 1. And for one more example, let's look at the limit as x goes to infinity of sine of x times the natural log of x. And we won't go to infinity here. We're going to go to 0 from the right. So this is actually going to be of the form 0 times negative infinity, because as we go towards 0 from the right, ln of x goes down towards negative infinity. And so, again, we need to rewrite this, and we need to rewrite it as some sort of quotient here. So again, you can pick either one you want to do this. I'm going to pick the sine. So the limit as I'm going to divide thinking of this over 1, and then we'll divide top and bottom by 1 over sine x, or 1 over cosecant, if you'd rather think of it that way. So we have ln of x over 1 over sine x. Now, to make this limit work out correctly, because if I go from 0 from the right here, I'm going to get infinity on the bottom and negative infinity up here. So I'm actually going to fudge this a little and make this a minus in both of these cases. And so one of the minuses I'm going to bring out front, and the other one I'm going to leave right here on the negative sign. And this is still going to be equal, but now I've fixed this problem so this is going to go off to negative infinity, and this is also going to go to negative infinity here. So what we want to do now we're able to use L'Hopital's rule because they're both going off to the infinity here. So we'll have negative limit as x goes to 0 from the right. And I can take the derivative of the top, which is 1 over x. And then we'll take the derivative of 1 over sine of x. And if you remember the derivative of cosecant, if that's something you have memorized, that's fine. Otherwise, you can just go ahead and use the product rule here. So what we'd have is the derivative of the top times the derivative of the bottom. So that'd be a 0 there, and then minus 1 times the derivative of the bottom, and that's cosecant. Then we have just sine squared on the bottom here. Okay. And so if we go ahead and sort of clean this up a little bit, we'll get negative limit as x goes to 0 from the right. And what we're going to have, if we wanted, so this is the 1 over x over minus, and that minus will turn that into a plus there. So we'll actually just have cosine of x over sine squared of x here as we simplify that. And we probably want to clean this up and see what happens if we do something here. So if we take this from the right here, well, we're going to get 1 or sine squared of x over x times cosine of x. And if we go ahead and look at this, what we get again is this is now 0 over 0. So we're going to have to do a little bit more work again. So we'll take and use L'Hopital's rule again. And so the derivative of the top, we'll use the chain rule. So we'll have 2 sine of x times cosine of x. And on the bottom, we'll get cosine of x when we take using the product rule. And we'll have then minus x times the sine of x. And now if we evaluate this thing, and plug in 0, because each time that's what we're doing. We're trying to evaluate the limit by just plugging the value in, because we're dealing with continuous functions here most of the time. So we're optimistic that just plugging the answers in will work, and we're getting these indeterminate forms each time. So now if we plug this in, we get the negative 2 sine of 0 times cosine of 0 over cosine of 0 minus 0 times sine of 0. And what we get there, so sine of 0 is 0, so the numerator is going to be 0, and the denominator, we're going to have 1 minus 0. So when we go ahead and do this, we get that this is 0. So this limit, when we take these two things multiplied together, is just 0. So the limit as x goes to 0 from the right is just of sine of x times ln of x is 0. And notice, again, it depends on what your function is, what's happening, because you can't just say 0 times infinity is infinity or 0 times infinity is 0. Because in our first example here, we found that the limit was going to be 1. And in this other instance, we found that the limit is going to be 0. And in different instances, you'll get different limits.